shear strain. So this, considering this shear parameters like viscosity, surface tension, pressure, radius, into just 5 key dimensionless parameters. This simplification.
Yeah, so figure 2 demonstrates, maybe I can turn on the laser pointer here.
Okay, otherwise I'm worried about I may have a problem, some student may have problem. But this class, what do I need to know? Most of the time I work on foam plastics. So I will use this as an example for the polymer processing simulation. But why foam plastic is an interesting topic. So look at this. We use this to reduce the weight of plastic, maybe to reduce the cycle time. However, I want to see if I can use this to reduce the weight of materials. On the other hand, how can I control the property? How can I control the property of this material? So, let me start with the basic information. And starting from 4 years ago, I started to look at the foam visualization. That means in my lab, I constructed two equipment. One is the static foam visualization. That means a batch process. I do batch forming, and I'm watching how does the cell nucleation and growth. The other one is this one. I'm using injection molding to create to observe the foam injection molding process. Starting from this, because some of you may not even have a background in fluid mechanics. So let me put it this way. If I start from the very, very basic of fluid mechanics, let's say if you have a fluid in between 2 plates, when there is no fluid flow, there are fluid in between 2 plates, and I'm pulling the lower plate with a velocity v. So basically, you are from no steady state to unsteady state, and gradually you will form a steady state because you are pulling it using constant velocity. Right? Some of you may already have a background, so don't feel worried because there are students who never take any material, any fluid mechanics class. So I have to make sure we are on the same page. And basically, because of that, here you have when you have a steady state, here you have a high velocity, lower velocity. So actually, you have a direction of momentum transfer. You are transferring momentum from this direction, from the y direction. And the boundary condition is y equal to 0, Vx of y equal to v, y equal to L, Vx of y equal to 0. Then I can define shear stress. So, first of all, most of you may have a concept of stress, right? Except those students from chemistry. I know 3 of the students in my class are chemistry major. But stress, the idea of stress is similar. force divided by area. Okay, force divided by area. This is the simple definition. But shear stress we can consider is a force divided by area, and this shear stress probably will be in proportion to the difference in velocity divided by the gap distance y. So let's say it's a minus dx dy. Then we say the tau yx will be in proportion to minus dy dvx. That's the basic concept of fluid mechanics. For shear stress flow in x direction, that causes momentum transfer in y direction. So you have a viscosity. We define viscosity. Here the viscosity is the shear stress divided by the rate of strain, or shear stress divided by the strain rate. Put it in this way. We just mentioned shear stress is F divided by A, and it's in proportional to one more time. Erase it. The shear stress will be in proportional to minus the Vx dy. So can we say this is rate of strain? Dvx dy is actually the rate of strain. Alright, how fast you are applying your strain. So the unit of this, what's the unit of this? The unit of this is 1/second, right? Because this is the distance over second. This is divided by time, and you are dividing it by distance. So the unit is 1/second. Then basically based on this shear stress divided by rate of strain, you get the where we were before. First of all, we are looking at this paper. Okay, this paper I think I already provided online. So we are talking about the study of dynamic foam growth. Okay. Don't worry, since the course content is super difficult, so you will not expect I will give you a super difficult final exam. So I'm trying to give you homework now. Let's see if I can give you a reasonable homework tomorrow. I mean, all the process, I just want to show you like I said, we should not just based on the final result to start the derivation or any numerical solution. So I have lots of problems with this. Then my motivation, simply because I want to learn something from this. So I started. Last time I think I finished until the momentum balance. Based on such a long hour, I think I finished the momentum balance at this moment finally I bring you this. Okay? This is the partial t partial r of t. Okay. Let me also ask you a question, a quick question. For equation 6, let me check. Okay. For equation 6, is it a function of time? For equation 6, I think the answer is yes. Okay, the velocity, surface velocity, is a function of location r and time t. Okay, because why I still mention about this, because we are going to interchange two concepts. One is the Euler point, one is Lagrange point. Okay, Euler point of view. Now I realize I need to keep using these 2 point of view. Euler point of view means that if you remember correctly, I mentioned about when you stand at the coast and you see the ship and you see the fish swimming in water. The other one, that means that you stand at the coast. You are standing. And Lagrange point of view means that you are swimming together with fish. Okay, we are going to use these two concepts interchangeably. So let's see what else I can proceed. Today I'm going to talk about something else. Okay, let's continue. Sorry, I made a mistake. This one should not be, because I used the mathematics to transfer all the mathematics into equations. So during the transform, some of the part is wrong. This one should not be equal. This one should be multiplied. Here, this one should be multiplication. Okay, so there is no equal sign here. There is no equal sign here. I will update. I will update. But some of the part, let me think about how can I explain more carefully. For this part, for this part, partial C, partial R, TO, differentiated with TO. How can I do? Let's use the relationship between partial TO, partial TTO, and partial TT new. This is the equation. Okay. So I'm substitute this one into this part. And here's the answer. How about the second part? I don't use the velocity. So it should be multiplied. Velocity multiplied by the, I know if you use the velocity, and velocity multiplied by partial r partial. And what is partial r partial? Partial r partial is 3 rho r squared. So should be this one. Right? I'm transferring partial r partial with partial x partial. So this is the one. Now, something I don't know. The natural log no dt. What is this? This is 1 over rho. This becomes rho dot divided by rho. And when we convert rho dot divided by rho into the equation, when we convert this one, you will find out at the end, all of the parts, these two terms cancel out. The whole thing becomes partial c x t nu t nu. And the whole equation at the end is this. I'm sorry. Then let's talk about right hand side. If we convert right hand side, the r into x and the partial r into partial x, the whole equation becomes this. This is the diffusion equation. However, this diffusion equation still, you have tons of questions. You have lots of questions to solve. Now let's go to the part we are going to talk about today. Let's quickly summarize here. Eventually, these are the 3 equations we need to solve simultaneously. 1, 2, and 3. Eventually, this is a summary of system. But now, one step further, I need to convert the diffusion equation into I. How do I convert the challenging equation remember, you don't like this because you still have an x inside here. Can we kick it out? Mathematically, can we kick it out? So let's see what we can do, okay? Let's see what we can do. And what is the boundary condition of this equation? First of all, let's explain what's the boundary condition of this equation. The boundary condition of this equation at x equal to 0 or I equal to capital of t at the interface C0t equal to what? HPG. Perry constant multiplied by the internal pressure PG, right? This one is acceptable. How about the other one? Since I said partial R, partial C equal to 0 at I equal to S of t, can I say that, sorry, this is small. I make it bigger. Can I say that when x equal to m, this one is also 0? When x equal to m, partial x, partial c equal to 0. Because m represents the whole envelope, or the mass of whole shell. Initial condition will be very, very straightforward. In the very beginning, what's the concentration inside the polymer fluid? C0. Yeah. Sorry, last time I was here, so The one I presented in the previous class actually was last week. So somehow I'm still get lost. I mean, not easy to do about coordination, transformation, all of these. You may consider all of these